Hi everyone, welcome to my next video, which is about liquid Relu and parametric Relu. So we have already discussed about Relu in the previous video. So let's see how we are going to solve the problem of dead neuron, which was occurring for Relu. So yes, so actually what problems we had in Relu. So for any negative value, so for any negative value, actually in the relu we are getting 0, so the graph would be for relu, like for relu we are getting graph is like that. So for any negative value, so for any negative value we are getting 0, because we need to concentrate on y while doing the graph of relu. Whatever value actually we're getting, we can simply see the y axis. So for any negative value, so we are getting 0. So for any positive value, we are getting that particular positive number. Supposedly we are providing input as 1 uh, to the relu function, so we'll get that particular 1 in the output, right? So this is relu, but in leaky relu what happens, that particular this particular straight line would be same, because for any positive value we are getting for any positive value we are getting that positive value in the leaky value, but in negative value we are not getting 0 here. As you can see, we are getting some like 0.01, 0.01 here, 0.01 for equivalent. So the dead neuron problem will be disappeared, because for any negative value we are not getting 0. So while doing the backward propagation, when you try to like when you try to multiply with the negative gradient, it doesn't provide 0. So the entire backward propagation doesn't go in vain. So it might occur like it we may get some vanishing gradient problem here in the liquid value, because as you can see, we have very low number of vanishing gradient problem may occur in liquid value, because uh, if we get very large negative values, like not very large but like very much large number of negative parameters, so we have to multiply 0.01 for each gradient. So if this 0.01 multiply number of times, it may goes to very small number of very what to say, very small number of gradient, very small number of gradient, so which may be possible to close to 0. So the it may hampers in the weight optimization. So the same vanishing gradient problem may occur if you have large number of layers which contains the negative parameters. So yes, but somehow it overcomes the dying relu problem, like dying relu problem from the relu. So yes, this is about leaky relu. So let's see about parametric relu. So parametric relu is nothing but so for all so for all positive for all positive value we are getting the straight line, the same positive number we are getting. But as you can see, we have for the negative value we are getting somewhat the uh, somewhat positive number for the negative input that we are giving to the parameter value. So this parameter is nothing but a trainable parameter. So trainable means it is learnable. So yes, if it is 0, if this parameter becomes 0, then it will be behave like it will behave like a value. As we can see, if this becomes 0, this positive value will just come. If this value goes to 0, so this straight line will just comes in that particular axis, so it will just behave like a value function. And if this parameter is 0.01, it will behave like liquid value that we have already seen. And it is learnable parameter, so it will try to learn by seeing the parameters in the neural network and try to develop any, like whichever the parameter required to get the maximum, or to get the minimum loss for the weight optimization. So yes, this is all about liquid value and parametric value. Okay, next is exponential linear unit. It is also advanced version of Relu function. It is exponential Relu. So as you can see the formula here, it is nothing but if for any positive value it will give you that positive number, same as Relu, Licky Relu and parametric Relu. But for any negative value or zero, it will just use this parameter. So it is nothing but alpha exponential minus 1. So the graph will be like that. So yes, so it is zero centric. As you can see, zero centric means it is one of the advantage, because for zero centric actually what happens, the gradient optimization, weight optimization would be easier for zero centric values, and will give values for negative pin unit. Yes, it will give you some values. As you can see, it will give you some values in the negative values as well. No vanishing gradient problem and dead value. So yes, it will not um, do the vanishing gradient problem. It will not uh, here actually we are not going to get vanishing gradient problem as well as dead ReLU, because in the backward propagation while doing the derivative, as you can see, we are not getting any zero here, so dead ReLU problem will not be there, and no need to find the derivative of zero, because uh, here actually in the derivative, as you can see, the derivative curve is not passing through any center or any origin. So the in real time scenario it is very much tough, or we cannot calculate the derivative of zero. So yes, this is one of the advantage for ELU exponential linear unit as well. So time complexity would be little much higher, because here actually we are using exponential values. So the time complexity would be more comparative to Relu or any other leaky Relu or parametric Relu. So okay. So next discuss about softmax activation function. So it is also mostly used because when we need multi-class classification, so we need to have softmax, because if we have binary classification we can use sigmoid activation function in the output layer. But when we are performing multi-class classification, we can or we should use softmax, because it will classify, it will give you certain range 0 to 1, or you can say it will try to give you the probabilities of the outcome of your classification problem. So this is the formula. So it looks like quite complex, but it is very simple. I'll show you one example through which you can get the idea of like how software function works. So yes, this is the basic neural architecture of three layer architecture. So we are providing an input image. Supposedly we are getting some of the values here in the output layer. Supposedly we are getting for this neuron actually we are getting 40. For second neuron actually we are output as getting 10. Similarly 20 and 5. So this is the value actually we are getting in the output layer. So if we are going to provide it to the software function, so what like how the output will come, supposedly it will just try to take the exponential of this particular first value, and take the and try to divide with the entire exponential values, as you can see in the formula here. So e to the power 40 divided by uh, e to the power 40, e to the 10, e to the 20 and e to the 5. So the value for 40, so this value, value for 40 would be 0.06. So we can write this 0.06. Supposedly it is a dog. Here for getting this image for being dog, it would be 60%. Similarly, we can take the value of 10, and we can take exponential of 10, then the entire exponential summation, then supposedly 0.02. Supposedly for cat classification, it is providing the image being cat image would be 0.2 and 20%. So similarly we can get for each values. So if you do the summation, it would be 1 because it ranges from 0 to 1. So if you do the total summation of these softmax values, you will just add up with 1. So whichever value would be large, the model will predict that particular value. Supposedly here for dog value, it is providing 60% chance or 0.6 as softmax function. So this image would be classified as dog. So this is it. This is for softmax attribution function. So thank you guys. Thanks for listening.